Swayam Prabha. Digital India. Educated India.
So, what I do is now I talk about soil nail wall. This is another elegant technique that that is because of the principle of reinforced soil that came up, and the principle is quite simple. What we do here is that in the case of reinforced earth wall, you construct from bottom, right. You just take you clear the ground and then put some this thing and put the facing first, then put the backfill, then put the reinforcement, like that. You have a sequential construction, you go from bottom to top. Here that is, you are constructing a wall. Here also you can construct a wall, but for an excavation, say for example excavation, what you do is that you come from top. The soil line consists of passive reinforcement of existing ground by installing closely spaced steel bars, which may be subsequently encased in grout. What we do is that we sequentially make a cut, make some little bit of excavation, put a nail, it can be a nail means a reinforcement bar, and it has some what you call the passive inclusions, okay, in the sense grout is there all around, and this is another one, like that you sequentially do that, okay. So, the construction proceeds from top to bottom, and we put either just a shotcrete or a shotcrete is applied to provide stability. The soil nail retaining wall, the properties of this material, native soil, like what soils can be used for nailing is another important thing, because soil is there and you need to strengthen it. It is in the RE wall, you get a backfill and then reinforce it. Here you have to deal with the existing system. So, native soil is there, you have to reinforcement is there, and facing element, the three things that are important, and the way that the three things interact, like nailing, facing, and native soil, that affects the performance of the structure. So, if you want to get the maximum benefit out of this, yes, you should understand three of them. I want to tell how the technique came. Actually, this technique came from in construction of tunnels. Actually, when you construct a tunnel, what happens? You make a small opening, and then there will be because of the opening there is a tendency for collapse, and the failure zone is like this, failure zone is like this. So, you try to design by means of arching action to retain this much amount of soil, you try to provide some reinforced concrete lining. That is the principle, where lat sigma r equal to 0, the radial stress line and all that, you do some traditional method, that is what people do. That is what they were doing, but in Austrian method, it is called new Austrian tunneling method. What they did was that many of the workers, the thing is that you put some nailing, short nails, so that it is stable, then put some simple cover. So, what is happening is that you did not allow this much of material to be acting, or you have not designed for this much of pressure, you only designed for this much of pressure, because this is actually, this is that pressure and all that. So, the advantage is that you are immediately able to, you did not allow the failure planes to develop. The moment you excavated here, you just put some nails such that all that vertical force that are coming, they are able to interact between the soil, because of the interaction between the soil and the nail, the load that is coming like this was much less, and you can have a thin facing, is it not? That is very interesting. And in fact, first nailing application was in 1972 for the railway road project in France. 18 meters is a high wall, you can see it's 18 meters is very big. And it was then in France, they started a big research program. It's called Cloud Terre. Terre means soil in French, and cloud means nail. So, soil nail is what is called. So, they started a big research program in the 90s and 80s. They worked about a very long time, say for example, about 10 years, and come out with a lot of guidelines. That is in the case of Germany. And in the case of the France, and in the case of Germany, they also did in 1975 one soil nail wall, and lot of research work was done again in the University of Karlsruhe and other places. And there are some companies that are doing even now very well. Actually, German soil nailing, you have to see, it's excellent. And in US, you have Federal Highway Document and soil nailing, and it was again, Giran and all, their persons who came from France, and then they helped them. And you have a updated version now, So, Federal Highway is also very active, and even in India, we have been able to develop guidelines based on some of the above, and Indian Roads Congress has made it available. In fact, I prepared actually, and we did that. Okay. So, what is this favorable conditions and unfavorable conditions for nailing? Actually, the thing is that you excavate, but if it collapses, it is a problem. So, you do not want it to collapse, right. So, but then you have to put the nailing also. So, if you can, if the soil can stand on its own for about half a meter or 1 meter before the nail is put, then it is fine. So, you can do that sequentially. That is what we try to do. So, critical depth is about 1 to 2 meters, and if it is there, it is fine. Second thing is, all soil nails within a cross section are located above the groundwater table. Okay, that is one thing that one should be very careful. And so, favorable soils are that stiff to hard and fine grained soils, dense to linearly with some cohesion and all that. And unfavorable soils like a poor graded soils, like which can start collapsing like that, or even water table, and very gravelly material where it is not even possible to, the thing is you are trying to provide a grouted soil nail. The thing is that you make a bore and then put a grout and put reinforcement, and if you can't make that in the gravelly deposit, then it is difficult. Okay. Organic soils, all that. What are the advantages? It is so effective that it can be used, with some space availability is quite less, construction is less disruptive to traffic, causes less environmental impact, relatively fast in construction, uses typically less construction materials and hence economical. Then occurrence of utilities may place restrictions on the location, inclination, length of the nails. What happens in most of the cases, suppose we are doing nailing in a town, important urban area, you have pipes, service lines, electrical cables, water supply lines and all that. So, that may put a limitation on the length of the nails in the upper areas, Then, when water table is there, again it poses a problem. Okay. Then it also needs specialized construction people, you need to have experience, otherwise it is very difficult. The thing is, the moment it collapses, see, you wanted it to be stable, but if it collapses, what is the use? So, it looks like this, you have a reinforcement rod, then you have the grout also here all round, then you can even have, there are some materials which is called, this is all grout. Okay. Centralizers is just to keep that in position, the thing is that there is a small centralizers to see that the whole thing is in position, and then you have geocomposite drain that can be used for drainage purposes, and then this is thickness of the temporary facing is about, say for example, 75 mm or something like that one can have, and then this is a permanent facing. There are all these things are done, and what we do is that we can just after putting the nail and it can be covered like this. That is what it. So, it becomes like a permanent wall. So, as I just mentioned, what are the steps? Go to some depth, then drill this equipment with some it is called wagon driller, and then put this nail bar and grout, and then this one, then shotcrete, temporary shotcreting, then go to the next level, placement of temporary facing, all that, next level, then 1, 2, 3, you can keep on going, then put this, and that is it. That is where we do it. So, these are all some applications of slopes. You can see here, big retaining wall structure. This is in the case of bridge abutment. You can see all round apartments here, but it was nailing is possible. In fact, I did couple of projects on these lines. This is our own underpass, IIT underpass, where these all nailed walls on either side, and the beauty was that if you have gone for a regular retaining wall, all the trees that were there here, 16 trees, you had to cut them, but then because of the nailing, it was there intact. This is another structure that we designed for the Ministry of Defence, about 7 meters high wall, shotcreting and nailing was done, and it was a very successful project which was finished in, whole structure was finished in a very fast time. It was very good. So, it received lot of appreciation awards as well. So, the soil layering technique has been well studied. In fact, so much so that we can classify them in field studies, and there is so much work by different people here. And people have started a lot of analysis, like analysis and design was well established, well studied, and Sosler, many people have studied Juran, and in fact, there are many people have done lot of analysis, Jewel and Pedley, there are very good work was done, there are many more, and soil nail interaction was also done, like how the soil interaction nail is there, how does it respond, pull out behavior, as I said, pull out is also very important actually. Then studies on numerical analysis and modeling, and in fact, there are so many papers. In fact, in some of these papers we studied effect of construction influences. There are some studies we did in this particular publication. All are very thoroughly studied papers are there, and again some more work on case studies we have, and reliability analysis also done. So, you also have lot of codes, BS 8006 code, TRL code, and there are so many codes available on these lines, Federal Highway Code, all that. And I will just describe what is presented in the Federal Highway Code, so that you can understand how you can go about design. That is what I would like to see. So, if you want to design a soil nail wall, okay, we should understand what are the failure modes. First thing, as we know, it is all external failure modes. We have to look for global stability, we should sliding stability, then bearing pressure, similar to any of the retaining walls or RE walls or anything. Then internal failure modes, it can pull out nail can come out, or the tensile capacity can be poor, that is 2 are possible. Then the facing failure is also possible, like it can bend, then it can punch, all that is possible, like we will see some of them. So, global stability, what it means. So, for example, we studied if this is a failure surface and this is a surcharge here, and you can assuming that this is a failure surface, one can derive an equation for equilibrium in terms of the factor of safety global, right. If you know the length C and then LF is the length of that, and reinforcement force required and all that, one can get that, and based on this one can derive that. and then the tensile force is distributed among all these reinforcement members, the horizontal component, and the allowable tensile force is there are two resistances here, resistance in terms of the tension and pull out, and the resistance in terms of the pull out is nothing but pull out is nothing, it is a surface area, right. If you are putting a circular thing, pi d LP into Q is the bond stress divided by 1000, whatever, it is just that. Then it is a tensile force, resistance tensile force is nothing but it is pi d square by 4, right, into Fy, so that is the total RT, tensile force. And the other important thing is that this is what we assume, particularly the code assumes some sort of the distribution of forces on the nail, like it varies from T naught to like this, and it comes to this, the length LP is here, and so we try to classify in terms of the RP is one term, that is called facing capacity, then RF is the nail capacity and the nail pull out capacity. There are three terms that we have, and so this is one important variable. And minimum factors of safety for global, temporary walls, if it is static it is 1.35, you include earthquake force into consideration and then you do that, it is 1.1. Permanent walls factor of safety is 1.35, of course there is no difference. Okay. Then what is sliding stability, like what the horizontal component of the forces and then this sliding force, it is a ratio, the sum of the ratio of resistances to driving forces. One can derive a simple equilibrium equation, and say for example you say here P equal to gamma h square by 2 into, like we know that already, P into gamma h 1 minus kV, if you have surcharge it comes like this, and this is in terms of the earthquake force, okay. And the K is the, if it is inclination, right, because it is somewhat sloping. So you have this factor of safety, again 1.3, 1.1, something like that, right. We are discussing this failure mechanisms of nailed walls. As I just mentioned, external stability is an issue, and apart from external stability we need to address some of the internal failure mechanisms. So, for example, nail soil pull out failure means if the length of the nail, say for example this is the active zone and we call it, this is a passive zone, and if the length is not adequate here, then the possibility is that the nail can come out easily. We do not want to have such problems. So, what we do is that we try to have adequate pull out resistance, which is given by this, like RP, which is nothing but the bond stress and the length of the length of pull out at any depth Z, and divided by the maximum tensile capacity at that particular layer. Okay. So, this is what we do, and we see that we know that the T max at any depth can be calculated in terms of the K into Qs plus gamma Z into SH into SV. This is very clear, and Qu is nothing but pi d Q into the drill hole diameter, okay, diameter. So, for example, the grout hole diameter is say 100 mm or 75 mm. We have actually drill bits which you can drill that and then put the nail. I just showed you the diagram in which you make a drill hole and put that grout, and also this equalizers are there. In the equalizer, nail and then both will be they will hold both of them together, and then they just see that nail, it should be at the center, right. To keep the nail in the center, that centralizers are used. Okay. So, this is what we do, and the length is nothing but, so once you know this, one can get this LP is nothing but, this is an expression because we use this failure mechanisms like this, we assume, and once you get this, the factor of safety has to be in temporary walls, static and dynamic, it is 2, and permanent walls it is 2, whatever, minimum factor of safety recommended. Then the other one that one can expect is tensile failure, like the factors, say for example, the tensile resistance available, and then the tensile force mobilized. So, it should be always more than 1, whereas RT is nothing but the area of cross section of that, and this is the simple, right. So, once you know that, again you have to see that the factors of safety of at least one point are maintained in static conditions, and whether it is permanent or temporary or whatever. So, one should see that tensile failure or the breakage should not occur. Then the other one is that the what you call the flexural modes, the facing failure modes, right. Failure modes are nothing but this, this sort of plastic movement formations, if it is too thin, it is possible to have, and even this sort of punching mechanism can occur, that is one possibility in the case of facing failures. Soil nail walls should be stable in external conditions, internal stability considerations as well as facing considerations, facing stability. These two are facing stability, and so you have to see that the factors of safety are ensured, and this factor of safety against facing failure is given by RFF divided by T naught. We will see that, and here this another one is given by these expressions. Okay, we will see that what is the tensile force that comes onto this, that is what we have to see. We will see that. I will just want to illustrate this with reference to some example here. 7-meter high wall. In fact, I have a lot of examples on this, in which we did even 10 meters, 12 meters, 15 meters and all that, and this is a simple example. And I want to tell you that there are two types of nails that we use in Bangalore or in India. One is called a driven nail, in which the nailing is done using a jackhammer. It just put it to the jackhammer and then drive nailing only, it is just a reinforcement rod, it just gets into the soil. Whereas a grouted nail is you have a driven nail that is there, and also the grout is there surrounded. The difference is that in the case of a driven nail, it is very easy to do, because cost and simple operations, that is what many people do in Bangalore, and whereas the grouted nail is much more rigorous, and it needs somewhat little expensive than the driven nail. And in this case, I am just using a driven nail, and the spacing is horizontal to vertical spacing is 0.5. In fact, our soil nail wall in IIC campus is made out of this driven nails, and spacing is like this. Okay. Then the inclination, sometimes people were using, it can be 25 degrees is the actual one, because that is what is an optimum degree, but in some places in what we use is just horizontal, because it is easy to drive a nail horizontally. Then the soil nail material is grade Fe 415, and this is what it is. Now, in fact, so soil type is dense to very dense sand, and cohesion is 0, and friction angle is like this, unit weight is this one. And ultimate bond strength, actually in one of the locations, in fact, I conducted a very field pull-out test, which is very low value that I got, and I am just trying to use it for demonstration purpose. Actually, that it is in an Ahmedabad area where it is just that it can easily, one can pull out the nail, the soil is so poor, and the diameter is 20 mm. So, I used, and then the bond stress is nothing but Q divided by pi into this. Okay. So, you get 47.75, surcharge is not there, and maximum force is given in terms of Ka into this particular factors. This is so you can see that it is 10.71 kilonewtons is the force required for this spacing, right, at a maximum spacing. Maximum depth of the, it is a small number. Now, the factor of safety for nailing tensile failure is 1.8 is what the code says. So, the required area of cross section is 46.45. You can calculate what is the area of cross section that you need to provide using these simple expressions with factor of safety and 415 grade and all that. And normally you choose a 20 mm because it is easy to drive. I can choose a smaller one, but I can't say 16 mm is also possible. So, you just provide this, and the area of cross section is much higher than this, very much higher. One can, in fact, 16 mm also can be done, but 12 mm is very difficult to drive, it's it can bend it. So, if it is very, if you can bend it, you can't drive it, there is, people have to hold it with some sort of arrangement. Okay. So, minimum length of the soil nail is adapted as L1 and L2. There is two considerations here, and so if we just use that, and at the top and 0.38 kilonewtons, and length that is to provide it is about 4.2, and so the 4.2 meters will be the length of the nail. It's 7 meter high, remember that. Okay. So, 0.6 is the one that we are using, and this is a normal thing that we provide actually. Okay. You assume that if 10 meters is height, 0.7 times into height, so 7 meters. It is 7 meters here, so 0.7 into 0.6 actually. 0.6 is also used. Okay. 0.6 into 7. So, there are some variations if the reference to this length. People are very like if you are using stiffer material like soil nailing, it can even go for 0.6. Okay. Geogrid's 0.7. So, there are some guidelines available, but in this case it is 0.6 into 7 is used, and so the length of the nails, and this is adopted driven nails of 20 mm and all that, this one fine. Now, the resistance against pull out is what you calculate, and LP you calculate, and at any point, and there is another thing RT, resistance due to tension is what you have provided. 130, because this is another force that you calculate. 131 kilonewtons is there in each 20 mm rod, that is what it means. Now, the allowable tensile force carrying capacity of all of the nail embedded at a depth Z is the minimum of RP and RT, and for SH equal 0.5 spacing, the equivalent you can calculate the depending on the spacing, what is that equivalent force. So, since we are providing for 7 meters 0.5 spacing, 14 length of the nails is 14, right, and at 40 at any suction, and so this is a location, you start with 0.25, 0.75 like that. Okay. Depth you can say 0.25, 0.75, 1.25, 6.75 like that, and the effective pull out length also one can calculate. It's at the top it's very less, because the failure wedge is just projecting, and the nail pull out capacity is quite low. Nail tensile capacity is very high, and the allowable axial, say this is a 2.11, it comes here. Okay. Tensile the pull out capacity is right. So, so like that one can get all this. The tensile capacity is same here, because 130, and this is the pull out capacity as a function of the depth it changes. Okay, because it's then you have this number, and then you sum up all of these numbers, see summation of all this 100.27. So, what we do is that, I think I will show you the previous one. So, this is what we have done. I mean, it is double of that actually, so there is no problem. Now, the weight of the failure wedge is 0.5 into gamma h square cot psi, all these numbers are given. Global stability factor, you have an expression here. So, use all of that equivalent tensile force and all that variables, you get a global factor of safety of 1.37, which is okay. Then the sliding stability that one can get is something, again this expression is there, bearing, and then active at pressure half gamma h square, weight and all that you have, and the sliding factor of safety is 1.77, all that. Then the soil pull out, nail pull out failure at any depth you have to see that, and this is the expression for factor of safety, and Tn is nothing but this expression we have, that Ka into that type 10.33 you get. Factor of safety at say for example at 6.75 meters depth level is then given by this expression 1.18. At the topmost point you can see that, yeah, actually it is less than the, it is a lower actually, less than the 1.3 specified actually. Okay, it is close to 1. I mean there is one thing we will see later. Soil nail tensile strength failure, the factor of safety against tensile strength is again to be calculated. This is that resistance available because of the area of cross section divided by tensile force mobilized, this 130 is the capacity of the nail, and then at each level, say for example, at 6.7 millimeter, what is the tensile force developed? 10.3, 130 is available and 10.3 is what is required. So, factor of safety is about 13, 12.59. Like that, one can calculate and then the tabulate all these results, and depth and all that. Only these two are little higher, and these are all very high. Tensile capacity, it's very, there is no problem, because you saw that what is required is just 10.10 or something. What is required is, what is provided is 131 or something. So, except here, at the top layers, there is a factor of safety is little less for the pull out. Okay, somewhat it's a little pull out is somewhat lesser here, because of that load that you have added there. What is the load? 300 kgs or very low load, which is something very unusual. But you can see that if it is little higher, if you just make it, I will just show you that. So, that is one important variable we will see. Then what about the shotcrete? Temporary facing design and checks. Calculate the design nail head tensile force at facing T naught. Actually, T max at that point is 10.71 and maximum spacing is S max is 0.5. So, there is an expression for the tensile force at the nail head. It is nothing but this expression, okay, 0.6 into this simple expression is here. So, 5.35 is a load that the facing should take care. Say some force gets transferred to the facing, this is the force that it has to take care. So, you have an adaptive wall facing of about 50 mm, and FI grade and M concrete and all that FCK welded wire mesh. The thing is that we put a wire mesh. See, the thing is that shotcreting, first thing is the nails are there, weld mesh is there, which is, say for example, 102 into 102 into 19 mm thickness, some gauge wire mesh. So, there will be welded and then shotcreting is done. Okay. So, that is what we do in our all structures, and many places it is done like that. So, once you have that, this is also another horizontal, the bars, horizontal welded bars, temporary facing, again we provide, like you saw in some places the welded beams being provided, and bearing plate is another one that we provide. So, what we do is that checks for facing reinforcement, the minimum steel reinforcement is provided, it is in terms of 20 into square root of FCK into Fy 0.21. So, this is another one that we provide, like in terms of the maximum value, it is minimum and maximum, it is say the reinforcement ratio, it is 1.42, it varies from 1.42 to 0.21 again. So, these are the two expressions. In addition, the ratio of the reinforcement in the nail head and the midspan should be less than 2.5. That ratio between the nail head and the midspan zone should be compatible ratio of the flexural capacities in these areas. Okay. So, that also, so verify the facing flexure stiffness RFF, we just calculate the facing flexure stiffness. This is another expression that you have in the federal code. Okay. These are little empirical, but at the same time, they are all based on, so RFF you have the due to flexural facing, resistance is what you are trying to calculate. Safety factor against is nothing but FSFF is nothing but this is a force 74 divided by the 5.35 is how you got, was that we will go to the previous step, the force that we have. Yeah, 5.35 is the force that you got from this expression, right. This is actually, as I said, if you connect the nail to the facing, weld mesh is also there. So, this material should be designed because all the some force gets transferred here because of the connection. So, how much of that force is, what is this, there is an equation that I just mentioned about a triangle, the distribution of the tensile force and all that, this is what you get, and the force that that can be used here. So, 74 is the force that you based on the spacing and RFF, there is an expression here that you have to use, and you will get this, and based on that the factor of safety against flexure failure is like this. Then punching failure is again there is an expression, simple expression for punching, which they have done based on mechanics considerations, and here also again same thing, you will get 11.97. So, the flexural stability of the temporary facing is all right, because the factors of safety are quite high, and you are essentially using these two expressions here. One is this one, and the previous one another thing I showed. So, the way that it looks like is that, as I said, the facing failure stabilities are quite good, temporary facing, and the minimum nail bar tensile strength, the reinforcement it is very good, right, it is an excellent thing. So, there is no problem. And global stability, see the thing is global stability is 1.37, it is close 1.3, and the sliding is also all right, and the factor of safety against pull out, if you put a driven nail, it is 1.18, right, we saw that, because I took some 300, but then the factor of safety increases to 3 if grouted nails with 30 kN per minute at 1 meter spacing are used. Like I did work out, revise all these calculations just for only that, because the pull out resistance is low there. The best way is to use the grouted nail, as I just mentioned, assuming that I have a 30 kN per meter length of the nail, just if what is the length of the nail here, it is 4.2 meters. If I just, so 4.2 into 30 is the total pull out load. Like if I just do a pull out test in the field, like pull out that nail, I will get the maximum load that I am expecting is 30 into 4, so 4.2, right. So, about 124 or whatever, right, 30 into, yeah, 30 into 4 is 120 plus what close to that point, so it is fine. So, suppose I get the pull out load more than this, I am very high, so I do a field pull out test which we have equipment, and it gets I get a load of say 100 kilonewtons, I will be very happy. Why? Because it is more than, say for example 200 kilonewtons I get total load. So, 200 kilonewton divided by length is 200 divided by 4.2, which is quite higher than what I used. So, it is fine. So, what I want to say is that the factors of safety can be increased very, like you need to design on these lines. Okay. So, that way the design has a look, global stability issues are satisfied, pull out resistance is satisfied, tensile capacity there is no problem at all, and then the facing stability is ensured. So, what is that you have to provide? So, thickness of the shotcrete is about 50 mm, and then M20 grade of concrete, and welded wire mesh and steel grade Fe415, this grid size 13, this is a small thing, and the other reinforcement baler beams one can provide, and bearing plate, this is another tape that one can provide, that what I showed you in the beginning, and once you provide this, that is fine, So, it is like what we do is that that constitutes a soil nailing design, and what I want to illustrate to you is that there are so many features in the soil nailing technique that you have to sequentially do the things, right. See, this is a simple design which is a conventional method, but the best way is to, like as I said, the effect of this nailing can be obtained, understood better in terms of finite element analysis. So, what I did was that we did a sort of finite element analysis, like typical example, what we do is that excavations, like I told you, in the beginning, like excavation E1, excavation E2, there are different stages, E1, E2, E3, E4 like that, you just remove that. So, what we try to do in this is that you try to simulate using a, you can use a flak or a plaxis or something and design this nail, what you do, excavate a bit, like say for example, you are putting half a meter, your spacing is 0.5 meters, right. So, space half a meter, excavate, then simulate that. What happens? There will be some plastic deformation zones stabilized, and you can still find out. So, after that put a nail and then check what is the tensile force mobilized, alloy it equilibrium and all that, one can do simulations, all that. So, you can do sequentially and excavation stages, E4, E5 are all the excavation stages and complete this annealing. So, in this case you can see that the factor of safety is global factor of safety, we are looking at it, the construction stage 1, 2, 3, 4, 5, right. So, the factor of safety is very high, it is a small cut you have made, it is not like, say if it is 5 meters, assume that 5 meters, just 1 meter is removed, the factor of safety is still high, deformation is small, then go to the next stage, factor of safety comes down. So, finally, at final stages, you have what is called strength reduction technique in Plaxis or even FLAC, you will get this number, factor of safety, and also deformations also one can calculate, and see as you go down, the deformations also increase, right. So, this is an interesting example of how you can get, because in conventional thing you do not have any information about deformation, right. If you want to get deformation information, and the thing is that you are assuming a failure mechanism there, right. You are assuming what type of failure mechanism, we assume a wedge there, it can be a logarithmic spiral, it can be a circle. So, what we want to do is that here in this finite element analysis or numerical analysis, you allow the failure mechanism to develop on its own and form the failure surface. So, that is much easier and much more better than assuming a failure surface and then doing the design. Of course, both are correct, but then the advantage is that you will get some information about deformations, the influence of construction sequence at every stage of excavation and all that. So, this is what is an example here. So, 15 noded some sort of examples we have taken, and the effect, it is a 15 noded triangular element, and Mohr-Coulomb model is used, and soil is a Mohr-Coulomb model, and there is some criteria for the simulation of nails as well, all that we have used, and we just want to give an example how the mesh density has a role, So, if it is a coarse mesh and a fine mesh, what happens? The global factor of safety, there is a 1.61. So, elements per unit volume is also used as a criteria. So, the factor of safety varies from 1.61 to 1.52, maximum lateral displacement 20 to 28, and the calculation time normalized with respect to medium mesh density. You take with respect to medium mesh density. What is the calculation? The thing is, if you make a very fine mesh, what happens? The calculation will take more time. So, it is 6.18 times compared to this one, you can see 1, and coarse one it is half of it, fine mesh this much. So, possibly you should take a balance, if you have a number of, and then see the accuracies involved, like 1.59 to 1.52 or so you have to see that differences. Definitely, if you want to go for good deformation predictions, you must go for fine mesh, there is no doubt about it, right. So, this is very important, that this gives an idea of the role of numerical simulations in soil annealing. Interface is also given, interface modeling, and how interface will affect the displacements and factor of safety. You can see that as the interface becomes rigid, the maximum horizontal force little comes down, and then this will increase marginally 1.7 to 1.78, deformation will also come down marginally, right. So, as I just mentioned, this will use essentially a strength reduction technique, which is given in the standard textbooks, and the advantage is that the Y, as I just mentioned, this is a failure surface, right, simulated wall, and in the Federal Highway we assume a distribution like this, okay. Critical failure surface from limit equilibrium, this is a failure surface, whereas from numerical analysis it is like this, which is like 0.3 to 0.4 H of that, and this is a tensile force, maximum tensile force, the way the distribution of tensile force developed, this is another important variable, and this is that facing, this is a wire mesh inside, this is the nail, and those things are welded, right. Other thing that I want to highlight to you is that the importance of using correct constitutive, appropriate constitutive models. Of course, this is not a course on numerical analysis, but at the same time I felt one should understand the influence of numerical modeling and ground improvement techniques. This just is taken as an example. For example, the height of the wall is 10 meters and grouted nails, then the spacing is also there, like 7 meters is the length of the nail, because I said 0.7 times height, length is some 15 degrees, spacing is 1 meter by 1 meter, spacing thickness and elasticity, all the properties are known. So, now actually the thing is that why these constitutive models are very important is that, normally we are using C and phi for representing soil, but when you are trying to do an excavation, the problem is that there is a bottom heave that comes up, there is a movement that takes place. So, there is so many if you do not predict this deformations properly, the building that is next to that will have a problem. So, it is important that one should apart from using a conventional method of calculation of nailing stability or anything for that matter in ground improvement techniques, one should calculate using even if you are capable of doing it, one should do using numerical methods as well. Like closed form solutions are fine, but you need to really much go beyond that and check because this will give a range of values. So, soil parameters, the thing is there are 3 types of models that suppose if I use Plaxis, I have 3 types of models which I can use. What is called Mohr-Coulomb model, the other one is called hardening soil model. Hardening soil model is similar to in the sense that the problems associated with soil are not just C and the soil parameters not C and phi alone. Soil has also the stress history effects, it hardens, and there is the confining pressure dependent behavior is there, like higher is the confining pressure, higher is the strength, all that things are there. So, if you want to capture them, hardening soil model is one thing, and then to capture the small strain, the thing is strain starts at not at what you see in triaxial testing, it starts at a very small level, two shear displacements of 2 soil particles. To consider that, they have what is called a hardening soil model, which is given in that small, it is called hardening soil model with small stiffness. And if you are using a FLAC also, you have the modified Kampfle model and all that, that can be done. So, these are all some parameters that have been used to get some information about the properties, like as I said, the soil has an loading and unloading behavior is different, right. So, to represent that, you have what is called unloading reloading modulus. Say for example, we know that the compression index is, say for example, Cc is some this thing, you have unloading there is another modulus. So, it is 5 times less actually. If you get a compression index of some say 0.4, 0.4 divided by 5 roughly will be the recompression index, actually why, because the soil is elastoplastic in the first stage, when you unload it, it is only elastic. So, it cannot completely recover all the plastic deformations cannot be recovered. So, what we do is that gets reflected in this compression and recompression lines, and even you can calculate them in terms of the stiffness, and these are all some parameters that we should use, and even the stress dependency, this is another parameter that you need to have. These are all one can understand, and the thing is that as a function of the construction stage, what happens with the different models was seen in terms of the global factor of safety. Like as you saw that the factor of safety is like little higher, like 3.8, and then it comes down to 1.5 or whatever, right. When the construction is complete, the factor of safety is somewhat in this range, and there is not much difference between the models used when you are trying to calculate factor of safety global. But when there is a deformation, right, there is a big difference. I want to highlight to that point, that you have Mohr-Coulomb model like this, hardening soil model like this, and another model like. What it means is that you are not estimating the deformations properly. That point I would like to highlight. Okay, that is it. So, Mohr-Coulomb model estimates the base heave, like these are what people have observed, and now normally we should use good constitutive models, otherwise there will be a serious issues of prediction of deformations in a wrong way like this. That is what I want to highlight. Okay. So, yeah, you can see that, yeah, what I want to Mohr-Coulomb model, the deformations are very high, let me repeat, and this is hardening soil model, and the small strain model it is like this. So, what I want to say is that if you use, see, most of the time the people use Mohr-Coulomb model for prediction purposes, but then the problem is that, you know, if you do not take care of the nonlinear soil properties like stiffness and small strains and all that, this deformations are overestimated. That is what I want to highlight. And when deformations are critical, one should use properly. Okay. Then the lateral displacements also the same, like, you know, you can see that this is another one that gives some information. So, there are some reasons for this, some of them, you know, these are all referred in some papers. And another important thing that I would like to highlight to you is that you have a tendency to calculate using Ka gamma z into Sv into Sh, right. How do you calculate the tensile force? Use this expression and then get tensile force. So, if you plot like this is a line you get, right. Then the thing is that this is from the depth of excavation. Okay. So, what happens is that if you really do from numerical analysis, you can plot them. What is the maximum tensile force? It is like this for different models. Maybe for Mohr-Coulomb model it is little less, but for other two models it is a little here. But then it is not the same as what we assume for design. It is less here, it is it is less here, it is more here. That is very important. Why? Because it is soil is not, see, there is no soil is, see, the thing is it is not like hydrostatic pressure distribution. What is that gamma H K N? It is a hydrostatic pressure distribution which cannot be like this. So, this is just a conservative assumption, but one should be careful at the top where one should be, you know, provide large pull out lengths and all that to avoid this problem of, you know, tensile forces are high, you know, compared to what you assume here. What it means is that there is a possibility of you know, pull out failure and you know, that possibility is there. So, you have to provide, normally reinforcement will not fail by tension, it is only by pull out. So, the if you provide short length and divided by tensile force, instead of using this tensile force, actually the actual tensile force is this much. So, there is a possibility of pull out failure. So, one should provide longer lengths here, that is what it means. Okay. So, this is about in terms of the construction stage, you know, in terms of the percent like when it is 100%, it is tensile force, you know, about 30 kilonewtons is what you have, okay, like 30 kilonewtons what you have. So, other thing that we have, you know, we have what is that length of the, what is the capacity of the 20 mm steel rod? I said it is 131 kilonewtons, right. We have seen that pi d square by 4 into Fy and all that, if you do, you get that. So, that 131, you know, you can just make it as a thin sheet, and if you are trying to do a plane strain analysis, you have to use equivalent stiffness, right. So, the moment of that bending stiffness have to be converted properly, and you can calculate how much is the tensile force, okay, and the factor of safety. Then the other thing that I would like to know, the other just I mentioned earlier in the beginning, you know, when I am trying to talk about the reinforced soil walls, stiffness of the material is also important. Like, you know, if you are using a geogrid, yeah, it can be a bendable material, you know, it is only acting as a tensile element. But if it is a nail or some stiff reinforcement like steel reinforcement, it has more bending stiffness. So, how do you understand that? So, for example, in this particular program, if I use a plate element, it takes care of bending moment. So, you have to bending moment and shear force are obtained based on that. Whereas, if it is just a geogrid element, which means it can only tensile element, then it can see that the factor of safeties are somewhat different. So, we use what is called plate structural element can be used to perform the analysis of soil nails considering bending stiffness of soil nail, as they require both axial stiffness and bending stiffness. Both axial stiffness and bending stiffness are required here, whereas geogrid elements can only have the axial stiffness. Okay. Axial stiffness is there are two stiffnesses that we have to give, and based on that and using the Mohr-Coulomb soil model, you can see clearly that the factor of safety in the case of a plate element is somewhat higher, particularly when you are trying to talk about in the beginning stages, like it is stiffer, right. Instead of 2.5, the factor of safety is little higher, which is a useful consideration. The same thing that you have, like particularly in the case of bending moment and shear forces, there is another one. It is only in the case of plate element, right, and displacements is another. Displacements will not be much different, and that is what you observe, and even that particular maximum force, like Ka into gamma h, you can even calculate like this and see that, why this is, the difference you will get it, if you do the simulations. And then T max in nails simulated using geogrid elements is found to be 15% more than that in the plate. And then so this is all the distribution of tensile forces. So, what you have seen is that what is the use of the numerical analysis compared to conventional analysis. I even want to go one step ahead, because what people have seen is the soil nail walls are supposed to be very good in earthquake conditions, and when they are like we have seen some earthquake coefficient specifications by Federal Highway and all that, and in this example I would like to show you, one is called the pseudostatic method, the other one is called time history. You can give the acceleration time history of the earthquake itself. What happens when you just do for any soil nail wall? This can be done for any structure, but this is just a soil nail wall is an example to highlight to you the role of numerical analysis in ground improvement. Because particularly why I have taken the soil nail walls, so that we do not have good guidelines on soil nail walls, and the fact is that they have withstood the many earthquakes, during many earthquakes of high intensity, the soil nail walls withstood the earthquake, and places like in northeast in India and all that, we need good stable structures. That is the reason why we thought we should investigate. And for the typical case, we took about 8 meters high wall, which is used conventionally designed using the allowable design procedure, like you can see that 8 meters and space cohesion and spacing is 1 meter and drill hole diameter 100 mm, all that calculations are given. And when you do the conventional design, the length is 4.7 meters, because the length is 8 by, that ratio is maintained, diameter is 16 mm, nail force diameter, all that factor of safeties, sliding, all that we have. Okay. So, once you have all these numbers, then the figures in the brackets indicate corresponding value from seismic conditions, putting kh equal to 0.106, okay, some kh value you have to put. And what happens to the maximum nail force? Instead of 40, it becomes 48, nail head 24, it becomes 29. The factors of safety slightly come down, 3.49 to 2.88, right. All these are well understood, right. Now, what I do is that we have earthquakes in our country, which which can be represented in terms of the time history, horizontal acceleration versus time. So, this is what one can do that. This is in Silchar and this is in Uttarkashi. So, these are all this data available, and data earthquakes and frequency and all that, right. So, what we saw is that, so we have static analysis, you have seismic analysis, which is in terms of the pseudostatic analysis, and also the time history data. You can see that, for example, the static case, the displacement is 0.67, what is the maximum horizontal displacement in terms of percent height, 0.61. Now, in the pseudostatic case, it is 3.29 in the case of Butch, 4.78 in the case of Silcher, and 5.24 in the case of Uttarkasi. And time history data 1.13, 1.54, 0.82. You can clearly see that the deformations are over predicted, is it not? You can see instead of 3.29 here, it is 1.13 here. Why? KH analysis assumes that earthquake is continuous and time history is constant, whereas there is a time history complete, it is that force is somewhat, it does not act, there is a dissipation, this earthquake occurred for a certain time, right, it has certain. So, you can see 4.7, 0.82. So, you can clearly see that a time history analysis of the earthquake and using it as an input for the horizontal force due to an earthquake is a better way of doing that. And of course, best is to do a conventional analysis actually, because the thing is that we should always do this and do that, this gives always a safer, to protect ourselves, that yes, I have used this method and it is I am giving a safe value, but this will tell you how safe you are to some extent if these calculations are correct. If you are wrong here, then it is very risky, right, but at least you cannot be wrong here, because in conventional method it is just calculations. But in finite element analysis, you can go wrong in numerical analysis and boundary conditions. One should be very careful. You may end up declaring, so one should always see that if you completely do this sort of analysis, it is possible to say where the numbers are falling. So, this is a typical analysis even in the case of static and time history and pseudostatic and theoretical. Of course, this is theoretical and Uttarkasi and all that, this is Silcher and all that. Response is similar, okay, that is fine. Yeah, displacements we have seen that how they are different in different loading conditions. If you take static, it is much lower, and time history it is little better, but pseudostatic gives somewhat higher, that is what we have seen. And very importantly, the tolerable seismically induced displacements like in the range of 0.63 to 1.25. How do you say that the structure is safe? In fact, I was telling you about the RE wall design, in which there is a horizontal force tolerance, serviceability requirements. It is about 1% of the height of the wall or some sort of thing, given that there is a some factor and all that. Based on that, if you can even say that, yeah, if even after the earthquake is subjected to, and if the deformation is in this range, then it is fine. You can in fact measure it. In some cases, if it would have failed, right. In some cases, you go to some earthquake conditions, I have seen RE wall failures are there, or soil level failures are there. If the deformation is there, yeah, it would have failed, and you can prove that yes, the deformation is much more than this 1%, so it has failed. You can say that, right. So, the other one that I would like to here the factors of safety are 0.81, right. Global factor of safety is 0.81, right. It is somewhat then 0.98 against pull out failure, and then this is another. So, these two are somewhat. What about the sliding? Okay, we will just see that. The length of the nail, I just was trying to say, original length is 4.7, and this is all the factors of safety. Okay, actual and federal highway codes are like this, and in some cases it has come down, right. So, what is recommended is 1.1, but it is 0.84 here. So, one can really alter that length and see what can be done, So, original is, so you can always change that and then get the improved length, and it can be done. So, one can, what I want to highlight to you is that the design issues that we have, okay. So, the design issues are very important, and in most of the cases, whether it is conventional design procedures for RE walls or soil nailing, they provide safe and conservative designs. In some cases it is true, but in some cases, like one should be careful also. That is why a lot of research is required to what extent this federal highway guidelines are complete, and in terms of telling, we talked about RE walls where the stress distribution is like this and 1:2, and is it correct for RE wall type of structure, all that can be examined. Provision of facing results in significant improvement of stability and performance of soil. Actually, deformation particularly is quite important. Actually, I was showing you one more example earlier in my previous class, where I was telling you about providing an offset at every level, okay, at some level, also helps in effective in reducing the lateral deformations. And then for soil nailed walls with rigid facing, the axial force developed at the nail head is generally 80 to 90% of the maximal force developed. So, in fact, what is the percentage of the nail force that comes to the facing is another important variable that you have seen. And in the dynamic analysis, we have seen that the spectral, like time history analysis, is somewhat very useful, and pseudostatic analysis gives somewhat a conservative estimate. So, what I would like to say is that soil nailing has been quite effective. In fact, I must tell you that there are a number of case studies that we did, like the other case that even I have, say there is one embankment structure, like it is a water reservoir, and where the water is removed from the tank, and what happened was that when the water is removed from the tank, because the water is full in some season, but then the village needs that water, tank, actually the town, actually it is not a village, it is a town that needs that water. When the water is withdrawn, the embankment dam has a clay core and a cover, so that clay cover, the cover was coming out. It happened once, it failed. Actually, the thing is that what people felt was that when the water is removing that cover, it means that the cover soil was erodible, like the erodible soil is somewhat erodible, and the possibility is that it can easily come out. So, people brought non-erodible soil and then tried to mix that soil and then used it. Second time again it failed. What happened was that between the clay core and the cover of the dam, there are some the interface shear stresses, and when the forces are of withdrawal are like that, it is just coming like that. And if you are able to stitch, I have seen that with the nailing, if you are able to stitch that clay cover as well as the core of the dam, it was working. In fact, that is a very unique case study that we did about 4 years back, and we stitched that clay cover with a core, with some overlap, about 5 meters nails at some spacing, and it is working very well even now, about even after 4-5 years of construction. Earlier it failed in 2004 and again 5, and people had a lot of difficulties. So, because they did not understand that the withdrawal also creates lot of forces, and there should be a lot of, to resist the shear forces, you need to have proper nailing force resistance for shear, and which can be provided with proper nails. So, with this I would like to conclude. Thank you.